Hello students, today I will tell you about the chemical properties of haloalkanes. So as we know, the nature of bond present in haloalkane is Rx. So this compound haloalkane gives many chemical reaction. So the very first is nucleophilic substitution reaction, and second is elimination reaction, third is reaction with active metals, and fourth is reduction method. So now first I will start with nucleophilic substitution reaction. So nucleophilic substitution reactions are those substitution reaction in which nucleophile attacks on the carbon part of haloalkane. First we know about what are nucleophiles. So when Rx means the haloalkane, that is Rx is the formula for haloalkane when it is treated with reagent like NaOH. So in this part, sodium hydroxide, this is positive part Na and OH is negative part. So the negatively charged species is known as nucleophile. तो यहाँ पर को जो आपका OH नेगेटिव है इसको हम nucleophile बोलते हैं. So this nucleophile attacks on carbon part of the haloalkane and forms the product. So इस तरीके से ही न्यूक्लियोफिलिक सब्स्टिट्यूशन रिएक्शन स्टडी करते हैं. जैसे इस पर्टिकुलर का रिएक्शन में अगर हम देखेंगे तो NaX is out from this and this is substitution because this halide part is substituted by this OH negative part and the byproduct form here is NaX. If we use Cl here, then NaCl is out from this. So the nucleophilic substitution reactions are those reactions in which nucleophile attacks on the carbon part of the haloalkane and forms the product. Now the first type of substitution is substitution by hydroxyl group or hydroxy group, formation of alcohols. So first alcohol is formed by haloalkane using different reagents like NaOH. If we use NaOH, KOH, this is aqueous medium. AQ stands for aqueous medium. NaOH, KOH and silver moist hydroxide, that is AgOH. All these three reagents give alcohol only. With the reaction with chloro derivative, instead of chloro we use bromo derivative as well. So haloalkane gives alcohol with the use of these reagents. So this is under heading substitution by hydroxy group because OH is introduced in the product formation and this Cl is out from haloalkane part. So that's why this is known as substitution, and substitution is taking place by nucleophile. That's why it is nucleophilic substitution. CH3 CH2 Cl when reacts with KOH, KCl is out, byproduct, OH is introduced on the carbon part, CH3 CH2OH is formed. And finally in this last reaction, similar reaction, CH3 CH2 Cl and AgCl is out as byproduct and OH is attached with carbon part and forms alcohol. So this is first chemical reaction, substitution by hydroxy group. Now the next substitution by cyano group, and that is known as formation of cyanides. Final product form here is alkyl cyanides, or cyanides are also known as nitriles. In IUPAC we use cyanide as nitriles. So this is again very simple reaction when chloro derivative or bromo derivative, whatever we use. CH3 CH2 Cl when treated with alcoholic, or we can simply write KCN, alcoholic solution of potassium cyanide, it forms CH3 CH2 Cn with the elimination of this. So all these reactions are very simple reaction because simple substitution is taking place here and it forms CH3 CH2 Cn with the elimination of KCl. Then similarly for bromo derivative, if instead of using Cl, if we are using bromo or iodine, all halo derivatives give the same product. Here in this case KBr is out from this and cyanide is introduced on the carbon part and it forms cyanides. Now the next method or the next substitution is by isocyano group, and that is known as formation of isocyanate. That is just opposite of cyanide, the previous case. So here haloalkane when treated with a specific reagent, that is silver cyanide AgCN, when CH3CH2Cl chloro derivative reacts with AgCN, it forms CH3CH2NC. And similarly when bromo derivative reacts with AgCN, it forms CH3CH2NC. Here byproduct is AgCl and here byproduct is AgBr. So a curious question come in our mind as why haloalkane forms cyanide group reacts when it reacts with KCN, CH3CH2Cl. When reacts with KCN, it forms cyano group. It forms CH3CH2CN. But when it reacts with AgCN, it forms NC. So this is very important question. So we have to know about this, because in this case, in this particular case, in the case of KCN, KCN forms purely ionic character in this, because it is K positive and Cn negative. In this both the atoms, carbon atom and nitrogen atom, both atoms are donating their electron pairs to carbon part of the haloalkane. But in this particular case, in AgCN is predominantly covalent in nature. So if it is covalent in nature, as AgCN forms a similar triple bond, but in this particular case only nitrogen atom, in this case, in the case of AgCN, only nitrogen atom can donate their electron to the carbon part. That's why it forms N triple bond C. So that's why it forms isocyanate instead of forming cyanide. So this is the basic difference between these two, the reaction of KCN with haloalkane and reaction of AgCN with haloalkane. Now the next substitution is by nitrite group, that is formation of nitrite, and substitution by nitro group. Again both reactions are similar to the previous one. Here in this, when alkyl halide is treated with potassium nitrite, KNO2, it forms CH3CH2ONO, or simply we write here in this way ONO, and this ONO suggests that this KNO2 is ionic in nature. That's why it forms ONO. And when haloalkane is treated with AgNO2, it forms nitro group, nitroalkanes are formed. So in these two cases, why haloalkane forms ONO with the reaction with KNO2, and why AgNO2 forms NO2 product as a major product when it reacts with haloalkane. So the reason behind that is same, because this KNO2 forms ionic compound and it gives R alkyl part O and double bond O. So this is the major product form here. ONO is the bond form here, that is known as nitrite, and in this case R and NO2 forms in this way, and double bond O and single bond O. So in this way nitro group and nitrite group are formed by these two reagents. Now the next substitution is by amino group, and that is known as formation of amines. So this is one of the functional group, alkyl amines. And second is also important, that is substitution by alkoxy group, that is formation of, that is another functional group, ether. Formula is ROR dash. So in the previous case, this first CH3CH2Br haloalkane when treated with ammonia, NH3 is ammonia, one of the hydrogen from this ammonia H and Br is substituted from this and form byproduct HBr, and the remaining part is NH2 is attached on the carbon part, so it forms CH3CH2NH2. This is known as primary amine, and the name of this compound is ethyl amine. Ethyl amine is formed. Similarly other members are also formed. It depends on the starting substrate. So formation of amines, first is substitution by amino group, then second is substitution by alkoxy group. So in this particular reaction we use particular reagent or specific reagent, alkoxide. The formula for alkoxide is RONA. So So this is the compound formula for alkoxide group and it is derived from alcoholic part. ROH जो अल्कोहल का फंक्शनल ग्रुप होता है ROH, उसमें से H रिप्लेस करके Na लगाते हैं तो RONA बनता है. R एक एल्काइल पार्ट है. So that's why the formula for this compound is C2H5, simply we write C2H5ONA. So when this alkoxide group is treated with halide, so this halide part Br and this sodium NaBr is out from this reaction, and this part CH3CH2, simply we write CH3CH2 as C2H5 and this O linkage. So it forms ROR linkage, that is the functional group formula for ether. C2H5O C2H5 is formed with the elimination of NaBr. So this is the specific method for the preparation of ether, and this is a name reaction known as Williamson synthesis. Williamson's synthesis. So this is one of the important reaction for the preparation of ether. So this is all about the substitution of amino group and substitution of by alkoxy group. So as there are so many other reactions in nucleophilic substitution, but these reactions are the most important reaction for nucleophilic substitution, and there are other reactions I will tell you later, these reactions and flowchart. Thank you.